Imagine a machine that can look at the swirling chaos of a hurricane, the erratic flicker of a flame, or the wild unpredictability of turbulent water and tell you, with startling precision, what happens next. Not for a few seconds, but for a long, long time into the future. And now imagine that this machine does something no classical supercomputer on Earth has ever managed to do, because it is not just a computer, it is a quantum computer. And what scientists just discovered about its ability to predict chaos is rewriting the rulebook on forecasting itself. For decades, chaos has been the final boss of physics and computer science, the one thing that makes weather forecasts fall apart after mechanics, and that makes even the most powerful supercomputers throw up their hands after a certain point. Chaos, in the scientific sense, does not mean random disorder. It means something far more frustrating. It means a system that follows precise, deterministic rules you can write down as equations, but this is famously called the butterfly effect. The idea that a butterfly flapping its wings in Brazil could, in theory, set off a tornado in Texas. Not because the butterfly has magical power, but because chaotic systems amplify tiny errors exponentially. And that exponential amplification is exactly what breaks every prediction model we have ever built, no matter how much computing power engineers throw at the problem. Classical forecasting tools, from weather models to financial simulations to fluid dynamics engines, have always struggled with this same wall because even a rounding error smaller than a single atom's width can spiral. This idea was first discovered almost by accident back in the 1960s by a meteorologist named Edward Lorenz, who was running a simple weather simulation on an early computer and decided to restart a calculation partway through by typing in numbers he had rounded off from a printout, only to watch the simulation diverge completely from its original path within a matter of simulated days. Lorenz had stumbled onto one of the most important discoveries in 20th century science, and the simplified set of equations he built to study that discovery, now famously known as the Lorentz attractor, became the standard testing ground that researchers still use today to benchmark any new chaos prediction technique, including every single quantum approach we are about to talk about. The mathematical fingerprint of chaos is often measured using something called a Lyapunov exponent, a number that tells you exactly how fast two nearly identical starting points in a system will pull apart from each other over time. And when that number is positive, you know you are dealing with genuine chaos, where tiny differences compound exponentially rather than fading away. Scientists have thrown incredible resources at this problem, building recurrent neural networks, long short-term memory models, known as LSTMs, temporal convolutional networks, and something called reservoir computing, which uses a fixed, complex, dynamical system to process time series data without the massive training costs of traditional deep learning. Reservoir computing, in particular, became a favorite tool for chaos prediction because it is fast and relatively cheap to train, but it has one brutal limitation that nobody could fully escape. And that limitation is memory, because to accurately capture a chaotic system, a classical reservoir computer often needs an enormous number of virtual neurons, sometimes thousands, just to represent the dizzying complexity hiding inside something like turbulent airflow or a churning ocean current. And here's where the story takes its wild turn, because a team of researchers, led by scientists at University College London, decided to ask a completely different question. What if you did not try to brute force the complexity with more classical memory, but instead handed that complexity over to a quantum computer, a machine that does not store information the way your laptop does, but instead exploits the strange, almost magical properties of quantum mechanics itself? To understand why this matters, you have to understand what makes a quantum computer fundamentally different from anything you have used before, because a normal computer bit can only be a 0 or a 1, nothing else. That is the entire alphabet it gets to work with. A quantum bit, or qubit, is not limited to just 0 or 1. It can exist in something called superposition, meaning it can effectively represent 0 and 1 at the same time, a blurry mixture of both possibilities until the moment it is measured, and that single. But superposition is only half the story, because qubits can also become entangled with each other, a bizarre quantum phenomenon where the state of one qubit becomes linked to the state of another, no matter how far apart they are, so that measuring one instantly tells you something about the other. When you combine superposition and entanglement across even a small handful of qubits, something remarkable happens. The number of possible states those qubits can represent together grows exponentially, which means a quantum system with only a few dozen qubits can, in theory, hold more information than all the classical memory on the planet combined. This is why companies like IBM, Google, and a growing list of well-funded startups have poured billions of dollars into building bigger and more stable quantum processors over the past several years, because everyone in the industry has been racing toward the same holy grail, a demonstration that a quantum computer can solve a real useful problem faster, cheaper, or more accurately than any classical machine ever could. And for a long time, that holy grail felt frustratingly out of reach. Early quantum advantage claims tended to involve highly artificial mathematical benchmarks, tasks specifically constructed to favor the strange statistical properties of quantum circuits, tasks that had almost no connection to anything an engineer, a doctor, or a climate scientist would ever actually need solved, which is exactly why so many experts in the field remained cautiously skeptical for years. This is exactly the property the UCL research team decided to exploit, and their approach became known as quantum-informed machine learning, or QIML, a hybrid method that does not throw away classical computers entirely, but instead uses a quantum processor to learn the hidden, underlying patterns inside a chaotic system, and then feeds that quantum-derived understanding into a classical AI model to sharpen its long-term predictions. The results, published in the journal Science Advances, were nothing short of stunning, because the quantum-informed AI system delivered roughly 20% greater accuracy compared to a purely classical AI model trained on the exact same data. And, in the world of chaotic forecasting, a 20% jump in long-term accuracy is a monumental leap, not a small incremental improvement. The quantum-informed method was about a fifth more accurate and remained stable over the long term in its predictions of how a complex chaotic system would behave compared to the AI model that did not use the quantum-learned patterns. But accuracy was not even the most jaw-dropping part of this discovery, because the quantum-informed model also achieved something classical models have always struggled with, which is stability, meaning its predictions did not degrade wildly the further out in time you push them, unlike traditional models that tend to spiral into nonsense the moment you ask them to forecast too far ahead. And then there's the efficiency angle, which might be the most practically important discovery of all, because the quantum enhanced approach required hundreds of times less memory than the equivalent classical system needed to achieve similar performance, which means you are not just getting a smarter model, you are getting a dramatically leaner one. This efficiency is a result of two quantum properties: entanglement, where each qubit can affect any of the others regardless of distance, and superposition, meaning a qubit can exist in different classical states simultaneously until it is measured, and these properties mean a quantum computer with only a few qubits still has massive computing power. Lead researcher Maida Wang, based at the UCL Center for Computational Science, described this as a demonstration of what scientists call quantum advantage, the elusive, hotly debated moment when a quantum computer actually outperforms what is achievable through classical computing alone. And in her own words, this new method appears to demonstrate that advantage in a genuinely practical, usable way, not just as a theoretical curiosity locked inside a physics paper. That phrase, practical quantum advantage, is a big deal in the world of quantum computing, because for years the field has been haunted by a persistent criticism, which is that quantum computers are great at winning contrived, artificial benchmark tests designed specifically to favor them, but terrible at solving real, messy, useful problems that actually matter to scientists, engineers, and businesses. This new research pushes back hard against that criticism, because chaotic fluid dynamics is about as real and messy a problem as you can get. It sits at the heart of weather prediction, climate modeling, aircraft design, engine combustion, ocean current simulation, and even how blood flows through the human body. The researchers specifically tested their hybrid quantum classical approach on simulations of turbulent fluid dynamics, the chaotic, swirling motion of liquids and gases that has frustrated physicists for well over a century, and is widely considered one of the last truly unsolved problems in classical physics. Fluid turbulence is not just an academic curiosity either. It directly determines how efficiently a jet engine burns fuel, how accurately a hurricane's path can be forecast, how blood moves through a narrowing artery, and how pollutants disperse through the atmosphere, which means even a modest improvement in turbulence modeling can ripple outward into massive real-world savings and safety improvements. And UCL's team is not the only group racing toward this frontier, because in a separate but closely related line of research, scientists have been developing something called quantum reservoir computing, or QRC, which borrows the reservoir computing concept from classical AI and rebuilds it using quantum circuits instead of classical neurons. Researchers behind one recent hybrid quantum classical reservoir study showed that combining the expressive dynamics of a quantum system with a classical memory layer can improve the prediction of complex chaotic behavior, using a 5-qubit transverse field Ising model to handle multivariate time series data drawn from turbulent fluid systems. Another team working on recurrence-free quantum reservoir computers, a streamlined architecture that strips out unnecessary recurrent connections to make the quantum circuits shallower and more hardware-friendly, demonstrated that their approach could reliably infer the underlying physical properties of chaotic attractors in both low and higher dimensional systems, which is a fancy way of saying the quantum model was not just guessing the next data point. It was actually learning the deep mathematical shape of the chaos itself. This distinction matters enormously because there is a huge difference between a model that memorizes patterns well enough to make short-term guesses and a model that captures the true underlying structure of a dynamical system well enough to make trustworthy long-term predictions. And the second kind is exactly what chaos researchers have been chasing for generations. To put that in perspective, imagine trying to predict where a leaf will float on a rushing river. A classical model might memorize that leaves near the left bank tend to drift toward the center, which works fine for the next few seconds. But a model that actually understands the underlying currents, eddies, and turbulence of the entire river can keep making sound predictions minutes or even hours later. And that is roughly the gap researchers are now seeing open up between classical pattern matching and quantum-informed structural understanding. It is also worth pausing to appreciate just how small these experimental quantum systems still are, because many of the studies mentioned here were run using as few as 5 to 7 qubits, a tiny fraction of the hundreds or thousands of qubits that future fault-tolerant quantum computers are expected to eventually contain. And yet, even at this almost embarrassingly small scale, these systems are already beating classical models on specific chaotic forecasting tasks. Yet another research group applied quantum reservoir computing specifically to discrete chaotic maps, including 2 famous mathematical models, known as the logistic map and the Hainan map, both of which are classic textbook examples used to study the onset of chaos, and their quantum system was able to not only predict future values with excellent accuracy, but also automatically distinguish between chaotic and non-chaotic phases of the system without being told in advance which phase it was looking at. That last detail is genuinely remarkable, because it means the quantum model was not simply pattern matching blindly. It was developing something closer to an internal structural understanding of when a system tips over into true chaos versus when it remains orderly and predictable, and doing so purely from the data itself. Now, here is where classical forecasting models start to look genuinely outdated, because for years, the gold standard tools for chaos prediction have been variations of recurrent neural networks, especially long, short-term memory networks, or LSTMs, which are specifically designed to remember patterns over long sequences of time. Researchers running head-to-head comparisons of different LSTM variants on the classic Lorentz attractor, one of the most iconic chaotic systems in all of physics, discovered exactly the problem that has plagued classical forecasting for decades, which is that tiny numerical errors get amplified exponentially the further out you try to predict. Because the Lorentz system has what is called a positive Lyapunov exponent, a mathematical measure of just how explosively small differences grow over time. Every single classical architecture tested in that kind of comparison, whether a vanilla LSTM, a bidirectional LSTM, a temporal convolutional network, or a hybrid convolutional and recurrent model, ultimately runs into the same wall, because no matter how cleverly you design a classical neural network, you are still fundamentally limited by classical memory and classical computation, and chaotic systems are, almost by definition, built to break exactly that kind of limitation. This is precisely the wall that quantum-enhanced approaches appear to be punching straight through, not by being infinitely more powerful in some abstract sense, but by representing the underlying complexity of chaotic systems in a fundamentally more efficient and more natural way, using quantum states instead of classical numbers. Now, it would be irresponsible to pretend this technology is fully mature and ready to replace every weather app and financial model overnight, because we are still firmly in what scientists call the noisy intermediate scale quantum era, often shortened to NISQ, meaning today's quantum computers are relatively small, prone to errors, and extremely sensitive to environmental noise, which can corrupt calculations if you are not careful. Researchers working on quantum reservoir computing have specifically studied this noise problem. And remarkably, some studies suggest that a certain amount of quantum noise, rather than being purely a nuisance, can actually be harnessed to improve performance in specific reservoir computing setups, almost like the messiness of the quantum world becomes an unexpected ally, instead of an enemy, a finding that genuinely surprised many researchers who had assumed noise could only ever be a problem to be minimized, rather than a resource that could sometimes be put to work. This idea connects to a broader theme running through nearly all of this research, which is that quantum computers do not need to behave like flawless, idealized textbook machines in order to be useful. They simply need to be good enough, stable enough, and cleverly integrated enough with classical systems to extract a genuine advantage. And that is a far lower and far more achievable bar than the one the field was chasing only a few years ago. Other researchers have focused heavily on robustness, deliberately testing whether these quantum reservoir systems can maintain accurate predictions even when the underlying quantum hardware is imperfect. And the encouraging news is that several architectures, especially the recurrence-free designs have shown resilience against decoherence, which is the technical term for a quantum system losing its delicate quantum properties due to interference from the outside world. So where does all of this leave classical forecasting models, the ones running inside weather, stations, financial trading systems, and engineering simulations right now, today, in the real world? The honest answer is that classical models are not obsolete, not yet. And probably not for a while, but they are undeniably starting to look like they are playing defense against a genuinely superior challenger, because every benchmark comparison so far has shown the quantum-enhanced or quantum-informed approach pulling ahead in exactly the metrics that matter most for chaos prediction, namely long-term accuracy, stability over extended time horizons, and dramatically reduced memory requirements. It helps to remember just how much effort the classical machine learning community has already poured into this exact problem, because engineers have spent well over a decade refining recurrent neural networks, experimenting with attention mechanisms borrowed from language models, testing convolutional front ends, and tuning loss functions specifically to squeeze out every last bit of performance on chaotic benchmarks like the Lorentz attractor. And after all of that sustained effort, classical architectures still run into the same fundamental exponential error growth problem baked into the mathematics of chaos itself. That is precisely what makes the quantum results so striking, because these are not incremental improvements achieved by simply throwing more computing power or more training data at an old problem. They represent a genuinely different strategy, one that sidesteps the classical memory bottleneck entirely by encoding complexity into quantum states, instead of trying to brute force it with ever larger classical neural networks. Think about what this could eventually mean for something as universally relevant as weather forecasting, where today's models start to lose meaningful accuracy after roughly a week or so, largely because of the exact same chaotic error amplification problem we have been talking about this entire time. If quantum-informed machine learning techniques can be scaled up from controlled laboratory simulations of turbulence to full-scale atmospheric and oceanic models, even a modest extension of reliable forecasting range could save billions of dollars in agriculture, disaster preparedness, aviation routing, and emergency response planning around the world. Climate science stands to gain enormously as well, because long-term climate models are essentially enormous, high-dimensional chaotic systems, and any technique that can squeeze more stable, accurate, long-horizon predictions out of limited computational resources could meaningfully improve our ability to project how the planet's climate will evolve over coming decades. Agriculture is another quiet beneficiary hiding in plain sight, because farmers around the world make enormous financial decisions, like when to plant, when to irrigate, and when to harvest, based directly on medium-range weather forecasts, and even a modest improvement in the reliability of those forecasts beyond the current handful of usable days could translate into meaningfully better crop yields and reduced water waste across entire agricultural regions. Aviation is yet another industry with a massive stake in this research, because airlines spend staggering amounts of money every year rerouting flights around turbulence and storm systems, and every extra day of reliable, trustworthy forecasting gives airline operations teams more room to plan efficient routes, save fuel, and avoid the kind of last-minute chaos that ripples through entire flight networks when a storm forecast turns out to be wrong. Medicine is another field quietly watching this space closely, because blood flow through the human cardiovascular system is itself a turbulent, chaotic fluid dynamics problem, and better computational tools for modeling. That turbulence could eventually help doctors predict dangerous conditions like aneurysms or arterial blockages, with far greater precision than current simulation tools allow. Energy production is yet another beneficiary waiting in the wings, because everything from optimizing wind turbine placement in turbulent air currents to modeling plasma behavior inside experimental fusion reactors depends heavily on accurately predicting chaotic fluid and particle dynamics, and fusion energy researchers in particular have been desperate for better predictive tools for decades. Even finance, an industry notoriously obsessed with forecasting chaotic, seemingly random systems like stock markets and currency fluctuations, has been mentioned by researchers as a potential future application area for these quantum reservoir computing here, because financial markets involve human psychology and unpredictable external shocks that are a different flavor of complexity compared to physical fluid turbulence. What makes this whole story even more compelling is the timing, because this is not some far-off theoretical proposal buried in an obscure journal that nobody will read for a decade. This is peer-reviewed, published research appearing in Science Advances and other top-tier journals throughout this year, meaning the quantum chaos forecasting revolution is not coming someday. It is already actively unfolding right now in real laboratories on real quantum hardware. Multiple independent research groups, from UCL to teams publishing in Physical Review Research, and the proceedings of the Royal Society have converged on strikingly similar conclusions from different angles and different chaotic test systems, which is exactly the kind of independent scientific corroboration that makes a discovery credible rather than a one-off fluke. One especially interesting piece of this puzzle comes from researchers studying how quantum reservoir computers behave when trained directly on real, noisy hardware rather than in a perfectly simulated environment. And they found that certain architectures remained insensitive to variations in the underlying quantum reservoir Hamiltonian, meaning the system did not need to be perfectly calibrated or perfectly identical from one run to the next in order to keep producing reliable, accurate predictions. That kind of robustness is exactly what engineers need to hear before they will ever trust a technology enough to build it into critical infrastructure like a national weather service or an airline's flight planning system, because real-world hardware is never perfectly clean, and a forecasting tool that falls apart the moment conditions are not ideal is not a forecasting tool anyone can actually rely on. Another fascinating thread running through this research is the question of optimal training, because unlike classical deep learning models that often require enormous labeled data sets and long, expensive training runs, sampled quantum reservoir computers have specifically focused on figuring out how to squeeze the best possible performance out of a limited number of measurements, which matters enormously given how expensive and time-consuming it currently is to run large numbers of experiments on real quantum hardware. One research group specifically demonstrated their recurrence-free quantum reservoir computer architecture on a 10-dimensional Lorentz 96 model, a more complex, higher-dimensional cousin of the classic Lorentz attractor that is specifically designed to mimic the kind of multi-scale complexity found in real atmospheric and climate systems, and found that their quantum approach could reliably infer physical properties of the chaotic attractor even in this higher-dimensional, more realistic setting. If you are wondering why this particular story exploded across science news outlets so quickly this year, it is because it hits a rare sweet spot in science communication, a genuinely surprising headline-worthy result delivered by a credible, well-established institution, published in a top journal describing a real practical improvement over existing technology, rather than another vague promise about what quantum computers might someday be able to do. And that phrase, practical quantum advantage, deserves one more moment of attention before we wrap up, because for years, critics of quantum computing have rightfully pointed out that many so-called quantum advantage demonstrations involved artificial cherry-picked problems specifically engineered to make quantum computers look good, problems with little to no real-world relevance. This new wave of quantum-informed chaos forecasting research is different precisely because it tackles a problem that scientists and engineers already care deeply about: turbulent fluid dynamics, using a hybrid approach that does not require a massive, fully fault-tolerant quantum computer to deliver meaningful results right now on the relatively modest quantum hardware that actually exists today. That last point cannot be overstated, because one of the biggest myths about quantum computing is that it needs to be perfect and enormous before it becomes useful, but this research suggests something far more exciting: that even small, imperfect, noisy quantum processors, when combined intelligently with classical AI systems, can already start delivering real, measurable advantages on problems that have stumped classical computing for generations. It is also important to stay grounded and avoid overselling where this technology currently stands, because these results, as impressive as they are, were achieved on carefully chosen test systems like the Lorentz attractor, the Lorentz 96 model, and controlled turbulence simulations, not yet on the full, sprawling complexity of an actual real, time global weather system with millions of interacting variables spanning the entire planet. Operational forecasting system is historically one of the hardest transitions in all of applied science, and researchers themselves have been careful to describe this as an early but genuinely promising foothold rather than a finished, ready-to-deploy solution. Still, the direction of travel here is unmistakable, because just a few years ago, the entire idea of quantum computers offering any practical advantage on a real scientific problem was treated with heavy skepticism by much of the research community. And now, in the span of a single year, we have seen multiple independent teams demonstrate measurable, reproducible gains on genuinely important chaotic systems. So what happens next? Where does this field go from here? And that is honestly one of the most exciting parts of this entire story, because researchers are already talking openly about scaling these hybrid quantum classical techniques up, from controlled laboratory simulations toward real-world weather systems, industrial fluid dynamics applications, and even larger, more complex climate models. There are still significant engineering hurdles ahead. Quantum hardware needs to keep improving in terms of qubit count, error rates, and coherence times, and researchers need to figure out how to scale these hybrid architectures without losing the efficiency, advantages that make them so promising in the first place. But the fundamental scientific proof of concept, the idea that quantum-informed machine learning can meaningfully outperform classical-only approaches on real chaotic systems, that proof of concept now firmly exists, published, peer-reviewed, and independently replicated across multiple research groups. Industry watchers, expect the next few years to bring a wave of follow-up studies testing these hybrid quantum classical techniques on progressively larger and more realistic systems, moving step by step from small laboratory-scale turbulence models toward regional weather patterns, and eventually, if the trend holds, toward genuinely global-scale forecasting challenges that today's classical supercomputers still struggle to handle reliably beyond a week or two. There's also a broader lesson buried inside this story that extends well beyond weather forecasts and turbulence simulations, because it demonstrates something important about how transformative technologies actually tend to arrive in the real world, not as a single, sudden, perfect leap forward, but as a series of hybrid, imperfect, incremental steps where an emerging technology first proves itself useful by boosting an existing classical system before eventually taking over larger and larger portions of the workload as the hardware matures. That is exactly the pattern we are watching unfold right now with quantum-informed chaos forecasting. A small, noisy, imperfect quantum processor working shoulder to shoulder with a classical AI model, each covering for the other's weaknesses and claims have started acknowledging that this particular line of research feels different because it is grounded in reproducible experiments on real hardware rather than speculative theory. And that shift in tone among the harshest critics is itself a meaningful signal. If you strip away all the technical jargon for a moment, here is the simple, almost poetic core of this discovery. Chaos has always been the thing that broke our best classical prediction. Tools, the thing that made weather forecasts unreliable beyond a week, the thing that made turbulence one of physics' most stubborn unsolved mysteries. And now, for what might be the very first time in a genuinely practical, reproducible way, a fundamentally different kind of computer, one that thinks in superpositions and entanglement instead of simple ones and zeros, is starting to outpredict the chaos itself. That is not a small story. That is potentially one of the biggest quiet revolutions happening in computational science right now, the kind of shift that rarely makes front-page headlines in the moment it happens, but that historians of science tend to look back on years later as the exact turning point where an entire field of forecasting quietly changed direction forever, and it is unfolding in real time, in papers being published this very year by researchers who are not hyping up distant science fiction promises, but demonstrating measurable 20% accuracy improvements, hundreds of times less memory usage, and genuinely more stable long-term predictions on problems that matter to climate scientists, aerospace engineers, doctors, and energy researchers alike. Classical forecasting models built the world we live in today. They power your weather app, your flight planning software, your engineering simulations, and they have served science remarkably well for decades. But based on everything researchers are now publishing, those classical models may be looking at the beginning of a genuine changing of the guard in quantum. Informed machine learning could be the technology writing the next chapter of how humanity predicts the unpredictable. If this kind of deep dive into where science and technology are actually headed is something you want more of, make sure you like this video and subscribe, because this is exactly the kind of frontier research that is going to keep reshaping our world in ways most people have not even noticed yet, and there is a lot more of it coming. The next time you check a weather forecast, or hear about a hurricane's projected path, or read about a breakthrough in fusion energy or personalized medicine, remember this moment, because somewhere in a lab right now, a small, imperfect, noisy quantum computer working alongside classical artificial intelligence is quietly learning to predict chaos better than anything that came before it. And that quiet revolution is only just getting started, so if you want to see where this goes next, stick around, because we are going to keep tracking every twist and turn of this story as it unfolds.